This is Physics 1020 and 1090. This is lecture for Wednesday, March 25th. Today we are reviewing for the exam. This is going to be going over practice exam 3A here in the first video. All right, so our first problem, and I want to just remind you that the order of the problems is randomized for each student. So this order may not be the same as the order for your exam, but they'll be the same problems, and all together, once we finish, you'll have covered all the problems in your exam. So problem number one is when you want to calculate the energy of a photon. Now, the wavelength lambda is equal to 30 microns. Let me just say one thing. With WebAssign, I can't use Greek letters. So when you have, the symbol is lambda, I'll just say wavelength. If the units are micrometers or mu-m, micrometers, I'll just call that a micron. That's its nickname. And I'll write out micron. So just keep that in mind. Reason I don't write mu-m is because I can't write Greek letters. So here we have 30 microns. Now the energy is going to be Planck's constant times the frequency. But the frequency is the speed of light over the wavelength. So put those together and you get the energy is going to be Planck's constant times the speed of light over the wavelength of light. Planck's constant, 6.6 times 10 to the minus 34 joules second. Speed of light, 3 times 10 to the 8th meters per second. And 30, the wavelength is 30, and convert it to microns, 30 times 10 to the minus 6 meters. Excuse me, convert it to meters. 30 times 10 to the minus 6 meters. And what you get is 6.6 times 10 to the minus 21 joules. Now the problem wants the energy given in electron volts. So you need to remember the conversion factor to go from joules to electron volts. 1 electron volt is 1.6 times 10 to the minus 19 joules. So you do that conversion, and what you find is that the energy of a photon is 0.041 electron volts. Okay, the other thing we need to remember is 30 microns is right in the middle of the infrared part of the electromagnetic spectrum. And 0.041 electron volts is not going to be able to break bonds. You need 10 to 100 electron volts to break a bond. 0.041, that's way too low to be talking about breaking bonds. So you end up getting 0.041 electron volts, that's infrared spectrum, cannot break bonds. Problem number 2 is a refraction problem. Okay, so we have over here, light coming from the air hitting a glass surface. Now remember, the light coming from the air is said to be 35 degrees. This angle is usually going to be specified relative to the normal direction or the perpendicular direction. And it's in air, which has index of refraction of 1. And it's going to come down and hit glass, index of refraction of 1.5, and it's going to be bent towards the normal. So your angle is going to be less than 35. It's going to be some unknown quantity theta that's going to be coming down here, again measured from the normal direction. This is a classic Snell's law problem. N1 sine theta 1 equals N2 sine theta 2. In this case, N1 out in the air is 1, so that's just 1, which I don't even write, times sine of 35 degrees equals 1.5, that's the index of refraction in glass, times sine of theta, the angle in the glass. Then you can just divide through by 1.5 and take the inverse sine. You get the angle is inverse sine of 35 divided by 1.5. And you calculate that out, you get 22.5 degrees. I want to just remind you, you got to know how to work your calculator. You have to make sure you know how to use your calculator, and you know whether you're in degree mode or radian mode. In this case, the angles are given in degrees. You should be able to do your sines and inverse sines, and if you should be able to get your angle out, you have to know whether it's giving you an angle in radians or degrees. Usually if it's in the degree mode, everything will work out in degrees. So that is problem 2. Problem 3 is just one of these color vision problems. Good news is it's not in the bad news is it's not in the book. The good news is there's not much to know really. You just have to know these basic color rules. That is, if you take a green spotlight and a blue spotlight and put them together so they overlap, you're going to get a cyan spotlight. That's a color, it's kind of a bluish green. Some other combinations that you need to know is if you take red and green and you mix them together, you get yellow. And if you take red and blue and you mix them together, you get magenta. I always find magenta particularly interesting because you can take a single wavelength of light, yellow light, and it'll excite both your red and your green receptors, but not the blue receptor, and it'll look like yellow. But there's no single wavelength that will excite the red and blue receptors, but not the green receptor between them. So you can only get magenta by mixing together two colors of light. You can't produce, say, a magenta laser. And if you have all three, red plus green plus blue, the three primary colors for light mixing, you get white. You can also do light subtraction problems. If you have a dye that absorbs, say, yellow light, then if you shine white light onto that dye, you will absorb the red and the green out, and what you'll have is blue reflected off of the page. So light that absorbs yellow reflects blue, and so on. So those are the problems with color vision. Problem 4 is going to be a thin lens problem. Here in this case, you have a thin converging lens, and it has a focal length of 110 centimeters, and an object distance is 80 centimeters. So the object's placed inside the focal length of the lens. Now, again, you don't have to draw the ray diagram. It's not required for the problem. I find it very useful as to check on my work. You have a ray that looks like it's coming from the focal point. It goes out straight. You have a ray that's going in straight and goes out through the focal point. You have a ray that goes through the center of the lens and passes through undeflected. They're all diverging out here. They appear to be converging at a spot over here, which is the image. Now we can do this analytically. We get a focal length of 110, object distance of 80, and we have the thin lens equation. 1 over f is equal to 1 over d object plus 1 over d image. Solve this for d image, and we get minus 293 centimeters. Minus sign for the object image distance is actually good because our sign convention has images over on this side being positive. This image is negative, so it's over on the left of the lens. Magnification is going to be minus di over do. The di itself is negative, so you have two negative signs that cancel. 293 over 80 gives you a 3.7. So you can just look at this picture without doing any calculations. You can say several things. It's a virtual image. The light rays don't actually meet here. If you put a piece of film here, you wouldn't develop a picture. But it looks as if, when you back extrapolate, all the light is coming from this point. So it's a virtual image. It is in the same direction as the object. It is upright, so it's not been turned upside down. And its larger image is larger than the object, so it's a magnified image. This is the classic case of, say, a magnifying glass where you have the object inside the focal length. The fact that it has a positive magnetization is consistent with it being an upright image. The fact that the absolute value of the magnetization is greater than 1 is consistent with it being a magnified image. Problem 5. Problem 5 is a thin film problem. So you have light coming in from the air, and it hits a piece of glass that has a thin film over the surface of the glass. So the light can either reflect off the air film interface, and that's that light ray, or it can come down here and reflect off the film glass interface and come back out, another light ray. You have two reflected rays, and we want to look at how much interference occurs between those two rays. So we're really looking at the interference here. And we're trying to find a non-reflective layer. We're trying to find a way to get destructive interference. So first thing you have to do is you have to ask yourself, are there any phase changes with reflections? Well, whenever you go from a low index to a high, you actually get a 180-degree phase shift. There's a 180-degree phase shift upon this reflection. But here you're going from the film to the glass, which is also low, 1.24, to high, 1.55. So you also get a 180-degree phase shift here. If you have phase shifts at both reflections, then the relative phase shift is not changed. The relative phase shift is unaffected if you do both the same thing to both rays. So what we have is no relative phase shift because of reflections, and we can forget about the reflections. So what else can give us a phase shift? It can if this ray has to go an extra distance compared to this ray. So what's the extra distance? Well, it goes down and then comes back. It goes round trip distance 2d. D is the thickness of this layer. 2d is the extra distance, and we want that for destructive interference to be some multiple of half integer of a wavelength. So it's half of a wavelength, 3 halves of the wavelength, 5 halves of a wavelength. Those are the conditions that will give us destructive interference, a non-reflective coating. Now remember when I say wavelength, that's actually the wavelength in this film. So that's the wavelength in the vacuum divided by the index of refraction of the film. So you can solve for D, and then you can solve for lambda. The wavelength is 4D N film over M. M's the integer. Now what the question asks for is a visible light in the visible spectrum that undergoes destructive interference and therefore gives you a non-reflecting layer. Well, really the way to do it is I just try to solve for various values of M. I'll start with M equals 1. If you do M equals 1, you get 670 nanometers for the wavelength. Well, that is in the visible spectrum. 400 to 700 is the visible spectrum in nanometers. 670 is just up here. It's up here at the long edge of the wavelength, but it's in the visible spectrum. So this one works. You might say, well, how do I know another one won't work? Well, what's going to happen if I go from 1 to 3? So it'd be 3 halves. So M is 3, and if you do 3, you'll get a third of this, and that's going to be down 200 and some nanometers. That's going to be out of the visible spectrum, down very shorter wavelength into the ultraviolet. And so will 5 halves, 7 halves, and so on. So the only thing that's in the visible spectrum is just going to be the M equals 1, and that's 670 nanometers. Last problem for practice exam 3A is a polarization problem. So initially we're going to have unpolarized light, and it begins over here as unpolarized. Then it goes through a polarizer. Whenever you take unpolarized light and goes through a polarizer, you immediately lose half the intensity. And now the light's polarized, parallel to this little line here, so it's sort of going back and forth like this, half the intensity. Now you send it through another polarizer that's 90 degrees to this one, so they're crossed polarizers. Well, it doesn't really matter what the intensity here is. If they're crossed polarizers, 90-degree difference between their pass axis, you're going to get 0 light coming out. So if you just have those two polarizers, you get nothing out. Well, now we leave those two polarizers there, but we slip another one in between. And let's see what happens then. Unpolarized light, pass it through the polarizer, you get 1/2, 0.5 times I0 times the initial intensity. So half is the amount of the intensity. Now, this polarizer is arranged so it's oriented so its pass angle is 15 degrees with respect to this one. So now we have to use our law of Malus. Says the intensity after the polarizer is equal to the intensity before times cosine squared of the angle between the two polarizers. In this case, the angle between the two is 15. So you take the intensity before, which was 1/2 times I0, and you multiply it by cosine squared of 15 degrees. Well, cosine of a small angle is pretty close to 1, so this is only going to be a little bit less than 1/2, and you get 0.467 in this place. But then it's got to go through this last polarizer that was originally crossed with respect to this one and never changed those two polarizers. And what I see now is that the angle between this pass axis and this one is, well, that was 15, and these were crossed, so that's 90, so the angle is going to be 75 degrees. So I take the intensity before, which is 0.467 I0, times cosine squared of 75. That's the angle between this one and this one. And cosine of 75 is a pretty small number, especially when you square it, and you end up getting 0.031 I0. So in other words, only about 3% of the original light gets through. But it's amazing anything gets through, given that those two polarizers are crossed. So you would expect nothing to get through if you just naively think of crossed polarizers. That's an example of a polarization problem. In the next video, we'll move on and we'll do the same thing for practice exam 3B.